Hello everyone, I am Charan Teja. This is my pattern recognition project. It is mainly based on analysis of speech recognition using frequency capsule coefficients. Moving on, what my project does. Firstly, we will know what speech recognition is mainly about. As you can see, the major division it comes in mobile and security applications because speech recognition today is very useful to differentiate the owner from intruder or the person who has your phone or a mobile. So speech recognition has many applications in that part of research. And this main differences what a speech recognition wants from you is a person has a different frequency when compared to another person, especially when he speaks out a word or a dialogue. So it has a limit of between 100 and 2200 hertz because that's the audible capacity capability range of humans. And the frequency is a unique feature which distinguishes a free speaker, as I told you already. Now let's move on to what my project actually does here. So here are the basics of speech recognition. Mainly, we can confine our basics to vocabulary, utterance, and accuracy. Vocabulary is a list of words that a system can distinguish. Like the basic words that we find in our dictionary or the vocabulary. What I'm referring to here, and the utterance is the pronunciation of a word. Because a person with a British accent or a American accent have a different utterance of words or intonations. It's very primal for a speech recognition software to differentiate two different accents because every two persons have different accents from each other. And this is where the speech recognition algorithm have to be accurate, and its ability should be to recognize the word correctly, even when the vocabulary and utterances are different from each other. So going on, as you can see here, my basic algorithm which I used here is a linear predictive coding. It basically removes the unnecessary sounds from the larynx, and then formant is a parameter associated with it. Every algorithm converts speech into a parameter and then uses it in the data flow. So after the conversion of the formant parameter, we can use it in the inverse filtering method, where the formant is removed and the remaining sound associated with the formant is moved forward to the data flow. So as you can see here in the block diagram, there is a pre-emphasis phase and then a frame blocking phase and then a windowing phase. As we go further, we can find the autocorrelation analysis phase, the LPC analysis phase, the LPC parameter conversion phase, and finally the temporal derivative phase. This is where we can find the output at the temporal derivative phase, or we can extract the output from the algorithm and use it to compare or map our sound with the actual user. So moving forward, as you can see, similar to LPC, the PLC algorithm is used, but more transformation are used based on psychophysics. There are mainly three feature vectors which are used in this algorithm. They are the critical band spectral resolution, equal loudness curve, and intensity loudness power law. So as you can see here, the algorithm is mainly divided, or the algorithm has a basic design flow as the given block diagram is. Initially, the speech signal goes into the Hamming window, and then the DFT analysis is done on that. Now, the outer middle card filtering is done, where you extract the signal from the data, and then it is sent to the gamma cape filter bank, and then equal loudness pre-emphasis phase. As you go forward into the data flow, we can find the inverse DFT analysis, where you inverse the DFT analysis and extract the data from your signal, and then finally the capsule recursion, where the extracted data is used to reconstruct the speech and map it to the actual person who used it. So this is how our algorithm works. It is similar to LPC, but a little different because it uses three feature vectors instead of a single parameter like formant does in the LPC. So now moving on to what my algorithm does, that's MFCC, that is the malfiltered capstrom. So human perception of speech is linear until 1000, as you already know. and logarithmic from there, because until 1,000 the perception of speech is not very variable, or variable in a linear phase. So when the perception of speech exceeds 1,000, that's when our logarithmic function comes in. So every capstrom is a Fourier transform. It is generally logarithmic because that's the unique feature a person can have after perception is greater than 1,000. So that is what we are going to exploit here in our algorithm. This is why we take a Fourier transform of the capstrom and then use these capstrom coefficients to extract our data and reconstruct the speech and then map it to the user who used it. So this is why capstrom coefficients are efficient than PLP and LPC because of their faster extraction technique. Now, moving on to vector quantization, we know that vector quantization is a clustering algorithm. It basically, quantizes a single point into a vector quantity that represents the properties of the point and the position of the point. So this is basically used for grouping by the k-means problem. This is done at codebook. As you can see here, it is a before vector quantization, where we can see all the lines or the speeches with different colors. But when vector quantization is done, that's when our points are converted into vectors, and every vector has different direction that represents each point. So this is where we can extract our data from, because we have two different or two unique vectors which have two different properties. So speech recognition will be easy if there are two different vectors that we can extract from. And now finally going into the conclusion, this is where all the above feature extraction methods are extensively analyzed, and I've come to a conclusion that MFCC gives better extraction, compared to PLP and LPC, for obvious reasons, because MFCC uses the capstrom algorithm, which is a Fourier transform. Because every Fourier transform we use is a logarithmic function, and it is basically very easy to extract from a logarithmic function, because almost every data set is a Gaussian. So logarithmic functions generally do a better job with a Gaussian data set. So MFCC is a faster method compared to vector quantization and FFT. So this is my project. Thank you very much.